Hello, welcome to another module in this massive open online course. So, we are looking at example problems for convex functions. Alright, let us continue our discussion. So, what we are looking at is examples, or rather example problems and in particular, we are considering this interesting function which is the log sum exponential, that is you have f of x bar is log of summation k equals 1 to n e raised to x k, and if we denote this by z k, that is each e raised to x k by z k, then you can write this as log 1 bar transpose z bar. Just to clarify this is the natural logarithm. This also you can write this as ln, okay, log to the base. This is log to the base e that we are considering. All right. So, by default, if you are not mentioning anything, then you can assume that it is log to the base e. We have computed the Hessian of this function, and that has an interesting structure. So, if you look at the Hessian, we have seen that this is diagonal of z bar divided by 1 bar transpose z bar minus z bar transpose divided by 1 bar transpose z bar whole square. And now what we want to do is we want to show that this is positive semi-definite, that the Hessian is positive semi-definite. Okay, remember we have already defined the symbol to which basically indicates that this matrix, the Hessian, is a positive semi-definite matrix. Okay. Now, to show that, we employed the straightforward approach, that is, consider any vector v bar and multiply this v bar transpose the Hessian times v bar, and this you can see, this is therefore substituting the Hessian, this is diagonal of z bar by 1 bar transpose z bar square minus z bar transpose divided by 1 bar transpose z bar square times v bar, which is, well, this is v bar transpose diagonal z bar into v bar divided by 1 bar transpose z bar. I am sorry, there is no square here, 1 bar transpose z bar, correct, 1 bar transpose z bar minus v bar transpose z bar times, well, z bar transpose v bar, but you can think of this as v bar transpose z bar transpose, and this is a scalar quantity, right. So, v bar transpose z bar is the same thing as z bar transpose v bar, or in other words, v bar transpose z bar transpose is the same thing as v bar transpose z bar. All right. So, it is the scalar quantity v bar transpose z bar times itself, or rather it is basically v bar transpose z bar square. Okay. So, this quantity is v bar transpose z bar square. And now, if you look at this quantity v bar transpose diagonal z bar into v bar, you can clearly see, or you can, it is very easy to see that this will be nothing but the summation over k Vk square times Zk divided by 1 bar transpose Z bar minus V bar transpose Z bar square, which is summation over K Vk Zk whole square divided by 1 bar transpose Z bar whole square. And if you simplify this, therefore, now further what you will have is, in the denominator you will have 1 bar transpose Z bar times summation K Vk square Zk into 1 bar transpose Z bar, which is nothing but summation K over Zk minus summation K Vk Zk whole square. Okay, and this is the quantity. And now to demonstrate that this is positive semi-definite, we have to demonstrate that V bar transpose the Hessian times V bar is greater than or equal to 0 for any vector V bar, which in turn implies that the numerator of this expression has to be greater than or equal to 0, and that is something that we are going to show in a straightforward fashion now. So, we want to show that this numerator quantity to show that the numerator is greater than or equal to 0. Now, for that what we are going to do is we are going to define 3 vectors. We have A bar equals V1 square root of Z1, V2 square root of Z2, so on Vn square root of Zn. We want to define another vector B bar, which is square root of Z1 square root of Z2, so on square root of Zn. These are 2 n dimensional vectors, okay, or you can also say these are n cross 1 real vectors. And now employ the Cauchy-Schwarz inequality, okay. Or the inequality for the inner product of vectors, which says that A bar transpose B bar whole square, that is less than or equal to norm A bar square into norm B bar square, alright. And now if you look at norm A bar transpose B bar whole square, that is nothing but summation K V1 square root of Z1 into square root of Z1, that is nothing but V1 Z1, similarly V2 Z2 and so on. So, this is summation over K Vk Zk whole square. This is less than or equal to norm A bar square, which is V1 square Z1 plus V2 square Z2 plus so on Vn square Zn. So, this will be summation K Vk square Zk times norm B square, which is Z1 plus Z2 plus Zn, which is summation K Zk. So, this quantity is less than, quantity on the right is less than or equal to quantity on the left, which means now you can simplify this as summation K Vk square Zk times summation K Zk minus summation K Vk Zk square. This is greater than or equal to 0, implies the numerator is greater than or equal to 0 or numerator of 1. Let us call this expression, this is what we have said to prove. So, let us call this expression as 1, implies numerator of 1 is greater than or equal to 0 implies V bar transpose the Hessian times V bar greater than or equal to 0 implies the Hessian is positive semi definite. Alright, this is the chain of argument. So, implies the Hessian is positive semi definite, implies f of x bar equals a convex function. Okay. So, f of x bar, which is the log sum exponential, is convex because we have demonstrated that the Hessian, first we have derived the Hessian and again in turn demonstrated the Hessian is positive semi definite. So, the proof is a little lengthy and tedious, but it has some very interesting aspects that can be used in general to demonstrate the convexity of functions, especially the convexity of functions of vectors. Okay. And sometimes these proofs indeed tend to be slightly involved. Okay. Let us proceed to the next example, and in fact this has several very interesting applications. This is used for if you look at the log sum exponential, this is the original function. This has a lot of in fact this can be used for logistic regression, that is to fit a curve to a given set of points, alright, and this has applications in machine learning and classification, as we are going to see later in this course. To classify a set of data points, divide them into two sets, one which corresponds to a response of 1, other corresponds to a response of 0. So, this can be used for machine learning or classification of data sets. Okay. All right. On that note, let us move to the next example, which is the following. We want to demonstrate that if f of x is convex, we want to show that 1 over x integral 0 to x f of t dt this is convex. We want to show that this is convex. For that we will use a simple procedure. F of x equals convex implies the affine precomposition implies f of Sx equals convex for each S. Now, we will use the property of the sum, that is if a function is convex, functions are convex, right. If you have several functions which are convex, their sum is convex. In fact, here we are going to use a continuous sum. So, this implies that if you take the integral, I can treat this as one function for each S. Okay. This is one function for each value of S. So, this implies that integral 0 to 1 f of Sx dx ds, this is convex. Why is this convex? Because this is a continuous sum, one function for each S, continuous sum over S for S lying in the interval 0 to S. So, this is basically a continuous So, instead of having a discrete sum, you have a continuous sum, alright. The integral is nothing but a continuous sum. And this implies that now In this you set Sx equals t, which implies that x times ds equals dt. So, this implies, now substituting this, so what you have is basically integral 0 to upper limit becomes s times x, which is t becomes equal to 1 times x. So, this is 0 to x, f of Sx is t, ds is dt by x, is, this implies that this is convex, which in turn implies that 1 over x, because x is a constant, integral is with respect to t, 0 to x f of t dt. This is convex. All right. So, this demonstrates that for if f is a convex function, 1 over x integral 0 to x f of t dt is also a convex function. Okay. Let us go to the next example, and in this we want to look at an interesting concept, and this is the concept of quasi convexity and quasi concavity. We have seen the definition of convexity. Similarly, one can define a set of functions which are quasi convex. Quasi convex basically means, so f is quasi convex if we define the set S of t equals the set of all x or x bar such that f of x bar is less than or equal to t. Okay. This is called a sub level set with respect to t. If the sub level set with respect to t if is convex, for all t, then f of x bar is a convex function. That is, if you look at the sub level sets of this function, what is a sub level set? That is, if you look at any parameter value t, consider the set of all points x bar such that f of x takes values less than or equal to t, and if these sub level sets with respect to each t are convex, the function is said to be quasi convex. This is important because there are several functions which are not necessarily convex, but qualify as quasi convex and can also have a lot of utility in practical applications. For instance, let us take a simple example. Now, if you look at square root of course, square root of magnitude of x. Okay. Now, you can clearly see this is not convex, correct, because if you take 2 points, let us say, right, and join them, join the chord. Now, function lies, part of it lies above, part of it lies below. So, it is neither convex nor concave. Okay. So, you can say function straddles the chord or function lies both above plus below the curve. Okay. And therefore, this is neither convex nor convex, because remember we said if the chord lies below it is concave, if the chord lies above the function then it is convex. So, this is neither convex nor concave. However, if you look at the sub level sets, that is if you look at any t, that is you take the all the set, all the points such that f of x is less than or equal to t, you look at the sub level set. Now, this set you can see sub level set the sub level set is convex, and you can easily see that. For instance, if you look at S of t equals set of all x such that square root of magnitude of x is less than or equal to t, this is equal to set of all x such that magnitude of x less than or equal to t square, this is equal to set of all x, which is basically minus t square less than or equal to x less than or equal to t square. And therefore, if you look at this set, this is the set between minus t square to t square, all right. And therefore, this S of t, which is basically simply the interval, closed interval minus t square to t square, this is a convex set. Remember, if convex set, if you take any 2 points in the set, join them by a line segment, it should lie in the set. So, minus t square to t square, in fact any closed interval, this is a convex set, okay. And therefore, this implies S of t is convex, and therefore, the sub level sets are convex. S of t is convex implies square root of magnitude of x. This is a quasi convex, quasi means not exactly, but something that can pass for, all right, something that is a quasi, all right, it is a quasi property. So, this is a quasi convex function, that is it is not strictly speaking convex function, but has some properties that are similar to that of a convex function, namely that the sub level sets are convex. Let us look at another example. For instance, if you look at A bar transpose x bar plus b divided by c bar transpose x bar plus d. Now, this is not a convex function, but if you consider the sub level set, this is less than or equal to t. This implies that A bar transpose x bar plus b less than or equal to c bar transpose t times c bar transpose x bar plus t times d, which basically implies that A bar transpose minus t, or you can also say A bar minus t c bar transpose x bar plus b minus t d less than or equal to 0. Now, if you look at this, this is nothing but this is some A tilde transpose b tilde. So, this is basically of the form A tilde transpose x bar plus b tilde is less than or equal to 0, implies level set. In fact, this is A tilde of t, this depends on t, right, this depends on the parameter t, implies. And now, if you look at this level set is nothing but a half space. Okay. So, the level set is a half space. We know that a half space is convex. So, all the sub level sets are convex, and therefore, this is a quasi convex function. So, implies S of t is convex, implies A bar transpose x bar plus b by c bar transpose x bar plus d. This is a quasi convex function. Similarly, one can come up with several other examples for quasi convex functions. All right. So, we will stop here and continue in the subsequent modules. Thank you very much.